All right, I want to continue with the problem that we worked last time, where we had the settlement of a structure here, and we had case 1, which was no basement, and then we had case 2, where we had an 8-foot basement here. And we concluded, after calculating the center settlement, in other words, the settlement beneath the center, the settlement beneath the center of the structure, we concluded that the settlement beneath the center was much smaller for case 2 with the basement than it was for case 1 with no basement. Well, now we want to look at the settlement beneath the edge of the structure. Beneath the edge of the structure. So that, we know sort of in advance what the settlement pattern is going to look like. In other words, we get this sort of dishing effect where the center settlement is greater than the edge settlement. And the reason for that is primarily due to the fact that the stresses beneath the center are greater than the stresses beneath the edge. So I want to work the problem, and for these two cases, exactly this problem, and now figure out what the edge settlement is. So this is an example, same as the previous one, but we're going to find the edge settlement. So it means what's going to change here. So when we have edge settlement, we're talking about point B beneath the edge, which is just beneath the edge. So if you remember, for case 1, we had ZF over B of 0.8, but now we're going to go beneath the edge in my diagram. And case 2, the ZF over B was 0.48, and again, we're going to go beneath the edge. So we use our pressure bulb diagram, and now the edge of the structure is measured over here. And for case 2, this is approximately 0.48. That's the ZF over B for that. For case 1, the ZF over B is 0.8, and it's approximately right there. And we're going to read off the contours. If we look at it here, for case 2, my contour is approximately 0.4. So I'm going to use 0.4 times our surface, the stress at the base of the structure of 200, gives me 80 psf for my delta sigma v. And for case 1, I'm here on this 0.3 contour, so it's going to be 0.3 times 1,000. Gives us 300 for our change in stress. And there's actually a little bit of an error here. And this should read B at point B. Okay, so our two numbers that are in our mind are 300 and 8. 300 is the first one, 80 is the second one, 80 psf, 300 psf. So when I look at my table, what do I find? Well, my U excess at t equals 0 plus now is 300. For case 2, my U excess at t equals 0 plus is now 80. So 380 are the two numbers there. The rest of the stuff is quite straightforward. My U is the sum of the U excess, U water table. And now we get down to the sigma V. Well, The t equals 0 minus figure is the same, so it's still 1900. My t equals 0 plus, what is it? It's going to be, well, that's the 1900 plus the 300 now. So we get 2200, and it stays the same at t equals infinity. Now we're going to be the 1900 plus 80, so 1980 stays the same at time infinity. And again, once I have my sigma v's, my sigma v prime is simply sigma v minus u, sigma v minus u. Take the columns I've already done. And again, I find that that's 1276. That's 1276 the same. 1276, 1276 the same. And then now I've got a sigma prime f of 1576 there and 1356 there. So again, now at this stage, the important numbers are my sigma prime I, my sigma prime f, and my sigma prime p, which we computed last time. Those three numbers. Sigma prime I, sigma prime f, and my sigma prime p. Those are the important numbers here. And I use those to create my graph. We have previously calculated the sigma prime p was 1353. That stays the same. So I put on the sigma prime I, sigma prime f, sigma prime I, sigma prime f. And in both of these cases, the sigma prime I, again, is to the left of sigma prime p. The sigma prime f is to the right of sigma prime p. And so in both cases, I have to use the whole equation, both slopes, that is. And so, again, I'm going to have 1353 over 1276 for that portion. Then I'm going to have 1576 divided by 1353 for that portion. Again, 1353 divided by 1276 for that. And then 1356 divided by 1353 for that. I get my epsilon v's, and then delta h again is h times epsilon v. And the h thickness was 20 feet. So I get 0.396 feet for my edge settlement for case 1 with no basement, and then my delta h, again using h epsilon v, I get 0.0308 for the situation with the basement. So notice again, the basement situation, much less settlement for the basement case. I want to introduce the concept of differential settlement. What do we mean by that? Well, I'm going to use the symbol rho for differential settlement, and I'm going to introduce this concept of rho over L, and an acceptable value, I'm just going to throw out a ballpark number of 1 over 300. And why do we have that? What does this all mean? Well, what is rho? Rho is the difference between the center settlement and the edge settlement. So in other words, if I look at my drawing here, I get this dishing shape at the bottom of my structure. For my case 1, I had 0.396 at the edge. I had 0.618 at the center. And the rho is the difference between those two. So the 0.618 minus the 0.396. So that gives me what we call differential settlement. The difference between the settlement at the center and the edge in this case. The L is the horizontal distance between those 2 points. And in this case, that's 12.5 feet because my building width was 25 feet. that gives me a rho over L of 0.0178 or 1 over 56. Well, 1 over 56 is bigger than 1 over 300, so we don't accept that. Similarly, for case 2, there's my center settlement, there's my edge settlement. The rho is the difference between the two. The L is still 12.5 feet, and so I get a rho over L of 0.00896, which is 1 over 111. And we find that both rho over L is greater than 1 over 300. So using that standard, neither situations is acceptable. Well, what do we do about that? Well, what can we do? Build a bigger basement. Build a bigger basement, we can reduce the settlement even more. So that is part of the foundation design. And I mean, there are other things that you can do to reduce settlement, but if you want to do it using a basement, you need a bigger basement for this particular case. Okay, I want to introduce another concept in the sense that what happens if we have, for instance, a very deep clay layer. So in this particular case, my clay layer is 80 meters down, or is a depth of 80 meters. I'm building a structure at the ground surface that has a width of 20 meters. And what we know is that as we go deeper and deeper and deeper below the structure, the soil feels the stress from the structure less and less. Well, when does it stop feeling it? That's the part of the question. So let's take a look at our pressure bulb, for instance, to give us some clues of and again, this is ballpark. This is ballpark numbers. Now what we see here, there's our pressure bulb, and here's our structure right there. And what we find is, if I look at this contour here, what am I at? That contour is 0.1. So if we consider that to be pretty low, anything deeper than that barely feels the structure. So in other words, if my point of interest is down here, well, I'm below the lowest contour, and for our conceptual study here, we're going to say that that's negligible. And we're going to say that soil down this deep is not going to feel the structure. And if we look at this, what do I see? I'm looking here, and what do I see? Oh, my contour here is approximately my 0.1 contour is approximately at a depth of 2b. There's my 2. So what we're going to consider, for the sake, to give you some gut feeling for what's going on in these problems, is that we are going to say that any soil that is deeper than 2b below the foundation, we're going to say that does not feel the structure, and therefore it does not compress. So we're not going to include that soil in our calculation. Well, what does that mean for our situation when we're looking at this particular situation? Well, here's how we look at it. Here's my structure with a width of 20 meters. So my pressure bulb, deepest pressure bulb, is going to be what? Well, 2B, which is 40 meters. So if I take that, I want to figure out where that pressure bulb is, and there it is, 40 meters. That's 2B. And so what does that mean? Well, then that means that I'm down here at 40 meters, okay, that means that the soil in this region, it does not feel the structure. So it doesn't compress, it doesn't get squeezed, it doesn't, nothing happens to it, so we don't include it in our calculation. So only the region of soil that gets squeezed is this region. And this region, so that's getting squeezed, that region has a thickness of only 30 meters. So in other words, when we're doing we squeeze only this part of the clay, and that part is 30 meters. So first of all, I use that as my H in my calculation. And so when I choose my point of interest, I want the center of this region. Well, where's the center of that region? Well, there's the center of that region. My point of interest is going to be there, not at the center of the entire clay layer, and just the center of this region. And since this total region is 30 meters, then my point of interest is going to be 15 meters down. And so the depth to my point of interest, you can see it from here, if that's 10 and that's 15, is going to be at a depth of 25 meters. So my point of interest in this case is at 25 meters, not the center of this, because this whole thing is 70 meters. And the center of that is in here at, what ends up to be, have to split that in half, 35 meters. So I add 35 and 10, that becomes at a depth of 45 meters. My point of interest is not at a depth of 45 meters. It is at a depth, it is here, because, why again? Because this is the region that is actually stressed, and that's the region that will compress. So I want to show you how to get this point of interest. For some reason, some students will stumble on this. And so I just want to emphasize the point of interest is not at the center of the clay layer. We're going to go 2B below 40 meters. And then I learned that my H is 30 meters. So my depth to my point of interest is 25 meters. And as I said, the point of interest is at the center of the squeezed region of clay. And so when do we need to do this? When the bottom of the clay layer is greater than 2B below the base of the structure, we have to do this sort of calculation. Okay, so here's how we do it. We're going to calculate 2B and draw the pressure bulb below the foundation base. There it is. And we're going to find two numbers. The depth to the bottom of the pressure bulb, we'll call it D sub PB. In this case, it's 40 meters. Okay, so find that. The next thing we want is depth to the top of the clay layer. Call that D sub TOC. Depth to the top of the clay layer is 10. And what we're going to do then with those two numbers is compute the depth to the point of interest, which is the sum of those two numbers divided by 2, because it's the average of those, the average of the top and the bottom. So we're talking about that's going to give us the depth to the point of interest. So just take that average. And then my H is going to be the difference between the two. So it's the 40 minus the 10, because it's just all I want is that distance H. So in this particular case, if I use these calculations, I get 40 plus 10 divided by 2, 25. And then that's just going to be 40 minus 10, 30. So they're easy to calculate. You need to get the h, you need to get the depth. So that's what this problem was. Find the point of interest and the h, the depth of the point of interest and the h. You need to know this. Okay, so I want you to know this simple calculation. It's important for a couple reasons. One, you have to have an understanding, a gut feeling for what soil is getting stressed when you build your foundation. So you're going to, once you recognize this, you're going to be able to come up with some clever ideas on how to solve your foundation problems. It's pretty handy to know. A pretty handy thing to have an idea of what you're doing, and then everything seems to make some sense. Okay, so here's another simple example. Find the h and the depth of the point of interest. And I've given you this information here. I've got a width of 40 feet, and I've helped you out a little bit. We have a structure with a basement here, and what do? I do 2B, 80 feet, draw my pressure bulb, and I can see that since that's 17 feet, this becomes 97 feet. Okay, so that's the given information, so you have that given information, and take a minute, half a minute, 30 seconds, whatever, to use those depths and find the h and find the depth of the point of interest. Okay. All right, I'm going to assume that you've done that. And here's the answer. Again, the point of interest is at the center of the stress clay region. And I use my two numbers, which is my 97 and my 30. And I take the sum of those two and divide by 2. I get 63.5. And I take the difference of those two, I get 67 feet. So in other words, on the figure, my depth of my point of interest is 63.5 feet. That's the middle. That's halfway between 30 and 97. And then if I take 97 minus 30, I'm going to get my h, which is 67. Straightforward, very straightforward once you have an understanding of what's going on here. So we just went through this, and now we're going to look at this in more detail, and I want to figure out. Eventually, we're going to. Well, let's start with these are the soil properties. So everything else has been given: the gravel and the clay. All the dimensions are shown, and what I want to do is I want to come up with my sigma v primes in this particular case. So what I want you to do, so here's my point of interest right there. I want you to fill in this table. So in other words, fill in these blanks, get your pressure bulb factor. I've helped you out a little bit there to figure out your Q. And what I want you to do is we have I haven't shown the t equals 0 minus picture. Well, I guess I have. Here's my t equals 0 minus picture right there. This is my t equals 0 plus to infinity picture, so it's a little bit bigger than the other one. So look at the t equals 0 minus picture up here to get that part, 0 plus to infinity, get that part. And okay, so pause the video here and fill in everything in this table. And fill in everything up here. Okay, I'm going to assume that you've done that, and now I'm going to show the answers. Okay, so let's start with this. My z sub f, remember, is the depth from the base of the foundation to the point of interest. So that's going to be the 63.5 minus the 17, which is 46.5. Then my ZF over B is going to be the 46.5 divided by the 40, which is the width. I get 1.16. And that means then I've shown the point of interest below the center of our structure. So what do I get for my pressure bulb factor? 1.16, I get a pressure bulb factor of 0.27. How does that come about? So 1.16 is what you have to remember. 1.16 is about in here somewhere. And what is it? It's between 0.2 and 0.3. So, I don't know, about 0.26, 0.27, something like that. Again, it's approximate, so. Oops. So, I took it as being 0.27. Then we get our Q. The weight of the structure was given to be 10 million pounds. And I guess I didn't point that out, but it's right there. Hopefully I had it here. Yeah, the weight of the structure was 10 million pounds. So I have 10 million pounds for the weight of the structure. I've built a basement that's 17 feet. I have to subtract off the weight of the soil there. 17 feet times 40 squared, that is the volume. And the unit weight is 120 for the gravel. Take the 120. And then I divide all of that by the 40 squared, the area. So I get a Q of 4210. Remember, I have my pressure bulb factor of 0.27. So what does that mean? When I do my UXS, again, at t equals 0 minus, it's 0. At t equals infinity, it's 0. At t equals 0 plus, what do I have? I got the 0.27 times the 4210. 0.27 times 4210, I get 1150. Again, that is the hardest thing to calculate. Water table, you can all do that. I'm showing the water table here at 20 feet. So I sum those two to get my U. So UXS plus U water table gives me U. And what do I do for my sigma V? Again, at t equals 0 minus, I'm going to look at my t equals 0 minus figure. And it's going to be, again, you can all do this, 20 times 120 plus 10 times 130 plus 33.5 times 110. I'm not going to go through that. That gives me my sigma V. Now now that we have this basement, to be honest with you, it becomes a little conceptually difficult. So I'm going to show you a different way, in a sense, to do this, so that you don't have to think about it quite as much. But it's okay to think about it, but it can be confusing because this has a basement now. So the way I like to do these this is very straightforward. In other words, I'm going to compute sigma V prime. How do I do that? It's just sigma V minus U. So I'm going to get this number here at t equals 0 minus. You can all do that. It's very straightforward. Well, what do I know? So I do this in this order. I know that at t equals 0 minus, it's 4671. Well, at t equals 0 plus, without even doing any more calculations, I know that this has got to be 4671. So so in other words, at this stage, what numbers do I have on my table? So I got my UXS, we did that. Got my U water table, I did that. I got my U's, I did that. I got my sigma V, I've got my sigma V prime. Then I get this sigma V prime. What's the next number I'm going to get? So, well, it's easy to fill this one in at this stage. Why? Because it's going to be the sum of the sigma V prime and the U, because that's what sigma V is. So I can get my sigma V by adding those two terms, I get 85/35. Well, what do I know? I know that the figure at t equals 0 plus and t equals infinity is the same. So that means my the sigma v at t equals 0 plus and the sigma v at t equals infinity are the same. So I write those down. And now I can get my sigma v prime at t equals infinity as simply sigma v minus u, which is 85/35 minus 27/14, 58/21. So for these problems with a structure in a basement, I sort of recommend this method of following. I've shown it: step 1, step 2, step 3, step 4, step 5. That's your easiest way to get these numbers correct without getting too confused of the concept with the basement. So that's what I recommend to getting these numbers. And then once I've determined that, I now have what? My sigma prime I, my sigma prime f, there they are. And then the other, if I want to calculate the settlement, I need sigma prime p, and I need the soil properties, which I haven't shown for this problem yet. Okay, I will stop there.